So, this is an eyeball shader I've been working on. It's kind of similar, it's kind of inspired by the eyeballs in the game Stray. I was sort of going for that, trying to recreate that, except I wanted it to be a little more fancy because I wanted, the eyelids themselves to also have some, um, they also have some sort of influence, when they follow the target object like this. And yeah, each eye has like its own. Yeah, there's blinking. Let's see. I can change the, like the pupil size of the eyes. Oh, give me a sec. Change like the pupil size of the eyes, like this. I didn't really do too much complex stuff with the eyes themselves. I was more focused on just the, the rotations and the blinking. Yeah, this was also sort of an experiment for instancing for me. So everything, each eyeball, like all the rotation data and everything is being calculated in a compute shader, and then that's being drawn. You know, everything is being drawn with instancing using the draw mesh instanced indirect method in Unity. So yeah, it was just like a test to see if I could optimize stuff and instance it, and how I would maybe go about that. And I didn't focus too much on like the eyelid texture. It's literally just a normal map and a color. Guess I'll just go through like the well, first, okay, if I was gonna make a tutorial for this, the first thing I'm gonna do is just create the basic shaders and Shadergraph without any without passing any parameters in from the compute shader or from buffers. And then after I get the initial materials set up and everything, or initial shaders set up, then I'll, I guess, work on their, then I'll record a start transferring everything over to the compute shader side. Yeah. Okay, so here's a blank for a new project, just default HDRP project. We'll create a couple folders real quick for shaders and materials. And then actually a lot of the, I guess, setup for this is done, in the modeling phase. I use the vertex colors to control the eyelids opening and closing, as well as you can also use the vertex colors for some like fall off if you want. Because we don't want, when the eyelid is like rotating, looking at the target object, we don't want the back of the eyelid to move with it. So we can paint in a fall off on our vertex colors if we want, using each channel. So in your 3D editor of choice, I use Maya, but I assume the same principles apply to Blender, all that, everything else. But yeah, like I said, there was a lot of setup in the actual model itself. So I also just used a default sphere like this, and then obviously modified it. But I started with this, so I actually open up our UV editor as well. So the first thing I did was just make sure our eyelid opens along the UV seam of this sphere. Let me add a few divisions so this lines up nicely. I don't think your sphere needs perfect topology, like your eyelid sphere would need perfect topology, but it does make it a lot easier, especially if you want to go the route of painting vertex colors in, because it's pretty easy to, just flood each edge loop with, a certain, or flood each vertex in that edge loop with one vertex color value, like in one channel. But yeah, I'm gonna line up the UV seam with the Z direction, the forward Z direction. Probably reduce the number of divisions as well, the height. So yeah, something like this, just a sphere. I have this, you know, I have a vertex in the very center. It doesn't have to actually have even divisions or anything. Like I'm not using the UVs for any of our displacement or anything. So you don't really have to worry about that. I just, you know, when you're modeling this, just it'll probably be a lot easier to texture if you have this seam, this UV seam right here, because we're gonna split the sphere along this, so each the top and bottom eyelids can rotate in opposite directions. So clear history, freeze the transforms, and then I'll just so I'll, what is it? I don't know, however you split split a model along an edge in your program. I'm going to use detached components in Maya. So now if I, so now I basically, so you know, now the sphere is split along this seam right here. Can like, just like grab the bottom edge, and you know we can pull that down. You can see how now we can rotate these two halves in opposite directions. But first, I will also extrude all the faces just by like 0.1, like this. Just so you know, our eyelid has some thickness to it. Okay, so now that you know we have the eyelid model shape. Well, I guess you could, you know, if you want the model to look a little better, you could probably like bevel this edge maybe, but I'm not gonna worry about that for now. I'm not trying to make this model look really good. This is good enough, I think. So yeah, so now in order to control the rotation in the most straightforward way possible, I just painted vertex colors. I stored the rotation info in vertex colors. Yeah, and we want the top of the eyelid to rotate backwards, you know, counterclockwise, and we want the bottom to rotate clockwise. And these rotations will have a fall off. It's, you know, the fall off will have a weight of 1 right at the lip, then it'll be 0 at the back. I know Unity has, you can download like a plugin, a tool to paint vertex colors if you want to do it in Unity. I don't know if you, I've never used it, so I don't know how easy it is to use, but in Maya I can use the apply color option, and then I can set colors per channel like this, which is very helpful. So I can grab, you know, an edge loop of vertices. Oops. And then just flood, you know, flood this with this red value, or this color for the red channel, this weight, for all these vertices. So yeah, I found that pretty easy. I mean, I'm sure there's like I'm sure there's plugins that exist that let you easily make it a lot easier, would make it a lot easier to set vertex colors, but all I'm gonna do is just go through my model and select this outer edge loop like that, and then its inner edge loop as well. That, and then I would flood this, or these vertices red value with 1, because this is rotating in the clockwise direction, so we're gonna have it positive. And then also I will set, so this is the bottom half of the eyelid. I'll go to basically the opposite side, like the inverse part of the eyelid for the top side, so that would be this edge loop of vertices right here. Also grab the inside vertices. So I have that edge loop right there. And the reason I'm setting this one equal to 1 as well is because since we want this rotation to be negative, but we can't store negative values in vertex colors, I believe. So we're going to set the red values of this going from 1 right here to 0 on the lip. Oh, you know what? Actually, these values should not be, whoops. These values should not be 1, they should actually be 1 step down from 1. So if you had like so in my case I have 12 steps because of how many edge loops I have. So I would just, what is 1/12? 1/12 is 0.083, so 1 minus 0.083 would be the actual value for this, or 11 divided by 12, so 0.916 repeating. So I'm going to flood these vertices with 0.9167 instead of 1. But yeah, once we flood the green channel vertices, we will, in our shader, we'll subtract the green channel from the red channel. So then, we'll get -1 up here and, 0 at the back. So we don't really need to do a lot of calculations in our shader to get the rotation working how we want it, is the goal of this. Oh, and this 0.9167 should also be set for this edge loop. It's just the opposite edge loop, basically. Well, I guess we could actually just select it like this. That, and then get our inner edge loop here. We'll flood that. Then we'll get our next edge loop. Make sure we're getting the inner and the outer edge loops. This one. And then, the value would be 0.916 repeating minus, whatever it was, 0.083, or we can just do like 10 divided by 12. But yeah, I'm just going to go through and set all the values for the red channel real quick. And all we need to do for the green channel is just, it's pretty easy. We just need to basically set the vertices in the top half of the sphere equal to 1, and the rest will be 0. So let me just, whoops. Let me flood the green channel with 0 to start, and then I'm going to grab all the remove these from my selection, and then just grab this top edge loop as well as the inner edge loop. Okay, there we go. So I'm not selecting this very back edge loop. Only basically all the top ones except for this very back one. Again, making sure I have the inside vertices selected as well. And then I'll just flood all that with green. And all we're gonna do, in our shader is just subtract the green channel from the red channel to get our rotation values for the, the eyelid. So this back value right here, since our red channel is 1, this will go to 0. This will be value of 0, then we'll get like negative 0.083 all the way up to negative 1 in the front where it's just green. I'll also set my, it doesn't really matter what these edge vertices are set to, but I'll set them to 0. And this is all we actually need to do for the setup on the sphere. We could, encode more information into our blue channel. If we wanted, you can create a fall off. At the back, we'd want blue channel to be set to 0, and then at the front, we'd set it to 1, but they can also achieve the same effect fairly easily using, the dot product with the forward vector. So I'm not going to worry about that, but it would, remove a few operations in the shader if we did, and just, read the blue vertex color instead. So name this something appropriate, like eyelid sphere. It could be more verbose. Say it has vertex colors as well. Then you can export it as an FBX, so it'll include your vertex colors and everything. Just make sure you get, you actually export the vertex colors with the object. So back in Unity, we can import our model. Let me create a folder for that. Okay. I'm just gonna uncheck all of Unity's default options. And now we can go ahead and create the shader graph as well. So just HDRP lit shader. We'll call it eyelid animated. I'll do it right. Eyelid animated. Okay. Then let me just create. When I make the eye object, I'm just gonna have an empty as the base transform, and then within that, I'm gonna have two child objects. One will be the eyelid, and the other will be the eyeball. So yeah, for the eyelid, I'll add the mesh components. That'll be our eyelid sphere. And the material we just made. So we'll open the shader graph. I believe all our default settings are fine for now. Change them later if we need to. The first thing you might actually want to do is just, get your vertex colors to make sure they imported properly. So just grab the red channel maybe and output that. And so yeah, you can see that we have the gradients applied properly, so that means we do indeed have a vertex colors, which is good. Okay, so now I will go ahead and work on the animation for the eyelid. And to do that, we're going to be using, a matrix, a rotation matrix to, well, we don't have to, I guess, for the, so we will use a rotation matrix for the look at target using that rotation, but for the eyelid opening and closing, we only need 2D rotation. we just keep our, if we look at this, we're only rotating around the x-axis. So all of our x vertice positions can stay the same in object space, and all we need to do is worry about the y and the z channels. So let's do that. We'll first get our object space position. These are all our object space vertices. And then we'll split that out, split it out, because we will need the x channel later, but we'll take the g, and we'll make a vector 2 with the y and the z channel. And Wikipedia is a pretty good source for looking at rotations, finding some good rotation matrix equations. So for 2D rotation, again, we're just gonna use this equation right here. X prime is equal to x times cosine theta minus y times sine theta, and then y prime is equal to x sine theta plus y cosine theta. And we'll also put this into a subgraph because we're going to want to use it to rotate our normals as well. So if we take this, again, our vector 2, split it out, the r is our y, the g is our z channel. So what we can do, so x cosine of theta minus y sine of theta. Theta is just, our rotation value, so we'll add a parameter for that. Call this eyelid rotation. And we'll need to take the sine and the cosine of this value. So we'll get these. And then we can multiply the cosine, well, we basically multiply each component of the vector by the sine and cosine. So first we can do sine, multiply that with the r channel, and multiply it the g channel, cosine, multiply with the red channel, as well as our g channel. Like that. And then, so we'll subtract y sine of theta from x cosine theta. So if we look here, g, we have that would be this. So this is again, y times sine of theta. Then we look for our x cosine of theta. So that would be right here. So we'll subtract this value. And then opposite to that, we just add them together. So we'll just add these two values. We might need to switch the operations for these depending on if our rotation the rotation for the eyelids is going the wrong direction. These could go down, these could go clockwise when we want to go counterclockwise. And then we'll just remake the vector 2. Output. Now that we have all this, I'm going to grab all the nodes we just made, including this split node down here. Like that. I'm going to right click, convert this to a subgraph. I'll just call this 2D vector rotation or something. Like that. Open the subgraph and just make sure we add a vector 2 output. And then I'm going to rename this to our rotation to theta, and then our vector 2 probably just stay like that. And I'll also put this in the output. Save that. So now we have this rotation. This is just a constant theta value right now, but we want this to be, applied per vertex with a per vertex weight. So we'll grab our vertex colors and split that out. And then remember, I'm gonna take our red channel and subtract the green channel from it to get, negative rotations up here and positive ones down here. And then we just multiply that with our theta value, or our eyelid rotation variable, and that's our new theta value. Like that. And then, so this was only our Y and our Z vertex positions that we're rotating. So we need to remake, the initial vector 3 also using our X positions. So we take the R channel from our initial split, split this. And then the R is our Y channel, G is our Z channel in this case. And we just rebuild the vector 3, and then this can go into our vertex position. But if we save this, oops. So this is a case where obviously something is wrong. So I believe I just need to flip these inputs, or these outputs, in our vector 2. And yeah, now it seems like it's good. It might still rotate the wrong way. I go to my material. And this is also also something I was worried about. So looks like I missed a vertex in my model, in my back in Maya. I did not paint this vertex properly, so I might have to go. I'm gonna go do that and then re-import the model again to fix that. But the rotation is working. It's just we're missing this one edge loop. I did not paint our vertexes properly. Okay, so I imported that, and that is now fixed. Rotation is working properly. Our normals are messed up because we haven't rotated the normals yet. Oh yeah, and you should probably also clamp this value so this doesn't go below 0. You can usually just clamp it in the 0 to 1 range like this, or however much you want it to open. So let me do that real fast. Set this to a slider. Yeah, just 0 to 1 range works. And then, so we need to rotate our normals as well. So we'll get our normal vector in object space. We'll split it out to the components, basically do this exact same thing up here, so we can just copy all those nodes, just switch the inputs around, like that. And then I will plug this into my normal vertex output. And then we probably want to put these in a category or something. So I'll call this eyelid open, open / close. It gets the point across. Let's save that. So now our normals are fixed, updating with our vertex positions. So that's good. And now the next thing we need to do is do the actual eyelid follow based on a target object. I'm gonna create, I'll just create a sphere for now. Oops. Call this target. But this target, again, like, you would most likely pass this to the shader through a script. it would probably be, you know, your player object would be your target object, but it doesn't have to be the player. It could just be, you know, an arbitrary vector 3 that you set, you know, to whatever you need it to be. Or like a transform in a script. If it's the player, you know, just the player transform. And you grab the position from that and set it every frame in a script, vector 3 position. But yeah, I'll just leave this here for now. And then back in our, just close the subgraph. Back in our shader, I will add a vector 3 that is the target position. Then this target position is again going to be the sphere position for now, just as like a placeholder until we, you know, set it to something else, like the player later on. And again, we're going to use a rotation matrix for this, for, you know, an eye follow rotation matrix pretty much. If we go back to Unity, or not Unity, go back to Wikipedia, they have a few different, there's actually like several different types of rotation matrices you can create. For instance, this one right here is one that involves yaw, pitch, and roll. Has 3 different values that get input to the shader, or to the rotation matrix. The one I want to use is the rotation matrix from an axis and an angle. The reason I want to do this is so that I can have an angle per vertex, you know, a theta value per vertex that controls how much that vertex will rotate or follow the target. So, you know, vertices right along the edge, like the lip of the eyelid, I guess you'd say, will, you know, be fully weighted, and then vertices at the back will not follow the target. And yeah, so this u value, this u is just the vector. Again, it's a normalized vector. And to implement this into Shadergraph, we could, like, you can use a subgraph, but, you know, if we look at this equation, this is a lot of operations, and doing that within a subgraph with nodes just gets really messy. It's very hard to keep track of. So I would recommend creating like a shader include file, an HLSL include file that just, we grab the method from there, or we you know, create the method in there, and that's what I'm going to do. So go back to Unity, back to our assets. Let's see, where do oh, I'm also going to make a folder here for subgraphs and put our 2D rotation subgraph in there. And I guess in our shader folders, I'll create another folder that will be shader include files. And to make an HLSL include file, we just create a normal shader file, like an unlit shader. I will name this, let's see, we can call this just shader helper methods or something like that. And then what you want to do is open this in your Explorer and rename it, you know, change the .hl, or change the .shader extension to a .HLSL extension. Also delete this meta file and it'll create a new one, the proper. So HLSL, yes, we will change that. Close that, and now we have an HLSL include file. We open this in Visual Studio. or whatever code editor you have and just delete everything for now. And so when we're creating a HLSL include file, the first thing we need to do is add an this if not defined at the top. You know, we say if this include file is not defined, then we will define it. Shader open methods. This is just whatever you want. This this can be, you know, whatever name you want essentially. And then we just do an end if. And we put all the functions we want to define inside of this define. And so what we want to do is calculate a rotation matrix from an axis and an angle. And you should also note that, you know, we're accessing this with a custom function node in Shadergraph. And all the you know, functions that you're grabbing with a custom function node from Shadergraph, all the functions need to be defined as type void. The function name, so rotation matrix from axis and angle. And in our include file, after we write out the function name, we also need to write it or type an underscore and then the precision of this function. So this would either be float or half or something like that. I'm going to use float. And you could also, you know, define another function with the half precision. But I'm just going to use float only. And then for an input for our oh, and if you wanted more info on the, you know, custom function nodes and shader include files and stuff, just, you know, you can check out the Unity documentation on custom function nodes. It'll outline some of the HLSL include stuff. But yeah. So we need two inputs for this rotation matrix, an axis and an angle, and then we'll have one output, which is a 3x3 rotation matrix. So for an input, we'll have a float theta, which is our angle, and a float 3, which is our axis. And then to define an output, we just write the out keyword. And then a matrix will be a float 3x3. And we'll call it rotation matrix. And so if we go back to Wikipedia to check the function definition, you know, we can see that we have this 1 minus cosine of theta value that is used in a lot of places. So again, we'll store that as a variable, as well as sine of theta and cosine of theta. So if we declare a float, just call this sine, or s for sine, and we'll get the sine of theta, like that. We'll get a float c, which is the cosine of theta, and then a float t, I believe it's usually defined as, for 1 minus cosine of theta. And then we can't directly just store our matrix values like this. We need to instead just declare a float 3x3 matrix, call it like M or something. And then we'll set all the parameters for M like this. So back in Unity, basically just gonna copy this whole rotation matrix, just row by row. So first we have the cosine of theta plus, again, here we'll grab our axis. Might actually rename this to something like A, just to make it easier to type out multiple times. So we have the x component of our axis squared, like that. And then again multiplied by this t value. So that's our first value in the matrix. Then we'll take the x component of our axis times the y component times our t value minus the z component of our axis times sine theta. Again, this is very just, just copying everything over. It's not hard. It's just don't want to make a mistake doing anything pretty much. This axis.y times sine. So those are the first three values in our matrix. Then I'm going to go down the line. Since it's a 3 by 3, helps to organize everything like this. Just go 3 values at a time across. So then we have the a.y times a.x times our t value plus a.z times s, or sine theta. We have cosine theta plus a.y squared times our t value, then a.y times a.z times t minus a.x times sine. Then on to our third row, we have the a.z times a.x times our t value minus a.y times sine. We have a.z times a.y times t plus a.x times s times sine theta. And then our last value is cosine of theta plus a.z squared times t. Like that. And then we will just set our rotation matrix equal to n. And then this function should be good to go. You can just save this. And then, so back in Unity, in order to access this function from our shader graph, we get a custom function node. The inspector, we'll keep this on file, and then we can access our shader helper methods here. And then we'll want this. We want to copy the function name without the underscore float, or the underscore whatever our function precision is. So we just paste the name in like that. And then we need to add the input and outputs to this. So we had a float theta and a vector 3, which is our axis. And then our output is the rotation matrix. Like that. Okay, so this function is good to go. And now in order to actually calculate our axis, we need 2 vectors, because we'll be taking the cross product. And so our object has a forward vector, the z component, basically, 0, 0, 1. And then we also have a vector from this target object to our eye object. And when we take the cross product of those 2 vectors, we'll get a third vector that we can use as our axis of rotation for the eyelid follow, if that makes sense. And normally, if we get 180 degree rotation of this rotation matrix, usually we'll get the axis will flip, the rotation axis will flip, but since we're going to be clamping our theta value so that the eyelid can only look within a 180 degree radius essentially, that won't be an issue. So to do that, again, like I said, first we need to get our target position, and then we subtract the object position from it. And this gives us the vector, or the delta from this object to the target, or the eye to the target. And then we want to normalize this, because it should have a length of 1. So that when we, take the cross product with our, we're going to be taking the cross product and the dot product with our forward vector. Dot product in order to get a theta value, and the cross product in order to get an axis. And we will also need to transform this vector from world space into object space, like this. And then let me also just get a vector 3. This is just our local object space forward vector with z set to 1. Yeah, I guess if your object, you could technically have your object set up to use x as its forward vector or something, but normally it's a z in most scenarios for the z-axis. So we'll take the cross product between these two vectors. I will need to normalize this again. And that is our axis of rotation for the rotation matrix. And then we will also take this transformed vector, direction vector, to the target, and take the dot product with our forward vector. And then, since the dot product returns a value in the -1 to 1 range, if the two vectors are normalized, obviously, which they are in this case, then what we can do is take the arc cosine of that, or the inverse cosine, and this returns a value from 0 to pi if our input is in the -1 to 1 range. I think 1 maps to 0 and -1 maps to pi, I believe, if I'm correct. But I'm not sure how how Unity's arc cosine function is implemented, but we can actually make there are some decently faster alternatives that we can use. You can just Google fast arc cosine equations. The one I found is just something I found on Stack Overflow. Let me see if I can. I'll put a link to it, I guess. But yeah, I'm just gonna implement it in a custom function, or not a custom function, rather I had it as just a subgraph previously, but it might just be better if we define it in here as a custom function. So I'll actually do that right now. Void fast arc cosine. It'll just take in a float. Call it theta again. Well, just call it x, because theta doesn't really make sense. And then what we want to do, and we also need an output, of course. Out theta. Oops, out float theta. There we go. And so what we're going to do is set theta equal to, and again, these are a lot of magic numbers essentially, but so first we're going to set theta equal to this number times x. This is just, like a cubic approximation. If you look at Desmos, if you look at the arc cosine of x function, this slope is, very similar to x cubed, or it has the same, it has the same shape essentially. This was negative, I guess, like that. And then you can see how if we just offset and multiply it by some values, then we can, approximate our arc cosine function. An arc cosine is somewhat expensive because it involves square roots. Usually it involves a square root operation, but we can calculate it. We can approximate it without a square root, so that's what we're going to do. So we have theta set equal to this. And we'll multiply it by x again. Subtract this value. Multiply by x again. And then we'll add like that. And this is a fast arc cosine function. We can actually look at it on Desmos as well to see the, just how accurate it is. So yeah, if we just graph the function the fast arc cosine function in Desmos, you can see that we get our intersection points at -1 and pi, at 1 and 0, which is good. And then where the graphs intersect the y-axis, 0 and pi over 2, so everything works out. And we don't really need a lot of accuracy with this because, we're just doing like a simple I follow script or function. So I didn't really, I was thinking I didn't really need a lot of accuracy for this. It looks fine if it's not, directly staring at the object, and you'll probably never even notice if it isn't anyway. So yeah, save that. Oh, I did also forget to add the precision suffix. Just make sure you add that. And then I'll just get another custom function. Use the same shader include file. And whoops. Type in the function name, fast arc cosine, and add our input and output to that. Oh, what I selected. There we go. Then we'll just put plug the dot product into that, and then we have our fast arc cosine function, and then here, well, if I go ahead and plug that in actually, since this is going from, this returns value 0 to pi, the Ri will be doing, we'll be doing full 180 degree rotations, but we could of course clamp this with a value, if we had a parameter to clamp it, which we will add. So eyelid rotation limit. Usually I set this to, pi divided by 2, pi over 2, 1.57, like that. But before I implement that, I'll just show you the flipping when, when we don't clamp the theta value. And of course to transform, so we also need to, of course, transform our normals and our vertex positions with this rotation matrix. So after we do open and close our eyelid, we'll then multiply by this matrix like that, both our normals and our positions, and then plug in these outputs into our vertex shader. Then we can save. Oh, and then of course we need to actually input our, we will have to, so for now I'll just make a default script for our target position, or we can just, change it manually for now. So temporarily I'll just make a script for our target object that'll set a global shader variable, or actually not even global, we'll just set this variable in our material. So let me create another folder for scripts. Create a C# script. Target update target position, I guess we can call it. And then we'll put a private material. This is just going to be our eyelid material. Serializing a field just makes it visible in the inspector, even if it's a private value. And then in our update method, and we should also declare a private read-only int variable. This is going to be the ID of the variable in the shader. So in our case, if it's this target position variable, it would be this underscore, this reference name is what we want to set when we're setting variables from script and shaders. So yeah, just look at the reference name for all your parameters if you want to set them through script. So in my case, mine is underscore target position. So I'm going to declare a private read-only int. Call this the target position ID. And I'll set that equal to a shader dot set, or was it property? Yeah, property to ID. This will just take a string and return, and get the unique identifier for whatever the property string is that we have. So we just set it to our target position variable name. And we want to set things using this property to ID because we don't have to keep, you don't have to do this unless it's a lot better to do this if you're updating something every frame and like an update method, because you don't want this to just keep having to recalculate the the ID for the variable every frame essentially. So then every frame we're gonna set a vector parameter on our material every frame, and this is gonna be again the target position. So the ID is the ID we just made, target position ID, and then the value will be our this script is gonna be placed on our target object, so we get the transform position of this object. Set it like that. That's all we need to do. Then go to the scene, add the script to our target object, get our eyelid material, and if we want to actually see this, you know, running in the editor, we need to add this execute always. This always execute always keyword above our class. Save. And now, you know, obviously our object is rotating. Of course, it's rotating in the opposite direction that we want. So we need to come up here and negate the value of our theta. And now we have our eyelid following the target object. Of course, if we rotate all the way behind, you can see how the eyelid will flip like that. But we're going to be clamping the rotation anyway. So in order to avoid this, and because it doesn't really make sense for the eyeball to do a full, you know, 180-degree rotation, in our case anyway. If you did want a follow script using, you know, without flipping, there are ways to create a matrix using, you know, you basically recalculate all your, well, you recalculate your x and y vectors in terms of this target position forward vector, and then create a matrix out of those 3 vectors. But again, the issue with that is that you can't really have it's hard to define a fall off for every vertex using that method. And you know, it's hard, like, it's not clean to just lerp between the old object vertex positions and new ones. But if you're not concerned about, you know, doing these rotations per vertex, then there are definitely better rotation matrices you can use that I would encourage you to look up. But for my case, I do want a theta value that I can have a fall off with for each vertex. So I'm using this, and then I'm going to clamp it. So before I negate our rotation value, I'll just take our rotation limit, and we can just take the max between, or sorry, not the max, we take the minimum between our, I think we take the minimum. I'm honestly not sure. Okay. So we have this, a rotation limit of our target, and yeah. So we take the minimum, and that just clamps our rotation. So the eye can't. I guess we do still get a little bit of a pretty sudden rotation when it crosses that threshold behind, but it's not, it doesn't do like a full flip like it did before. That works. Clean this up a little bit. And then of course, the next step would be actually calculating a fall off for that, you know, rotation theta value. With like a value of 0 at the back and value of 1 at the front of the eyelid. And to do that, we can just use the dot product between the forward vector and the position of each of our object, or of, you know, yeah, each object's vertex, each vertex position. So I'm just going to grab our object space position again. I will take the dot product with the forward vector, which is, you know, 0, 0, 1, like this. Oh, we will also need to normalize these vectors, object position vectors, and this is again why, you know, you might want to just encode this information in your object's vertex color, like blue vertex color channel. I was just too lazy to do that. Anyway, so we have the dot product. This is in the -1 to 1 range, so we want to add 1 and then multiplied by 0.5 to put it in the 0 to 1 range, and then we can just multiply at the end here our theta value, multiply it with this mask, and then put that into the theta. And now if we move this around, you can see how the, how we're getting a fall off. Yeah. Just the vertices towards the front of the eye will follow the target object more than the ones in the back. And we can of course, add additional variables like could add something like an eyelid follow strength variable like this. I'll make this a slider of 0 to 1. I'll set it on 0.5 as a default. And we would multiply this value. This is again our mask. It's in 0 to 1 range. So multiply it by 0.5. Now it's in the 0 to 0.5 range. Like this. So now, our eyelids won't, or the eyelid will not follow this quite as heavily, and if we put it to 0, then it won't follow it at all. If we put it to 1, it's back to the max. Like that. I usually leave it at like 0.5, looks pretty good to me. But yeah. So that is the eyelid follow. So I'll group this. Eyelid target follow or something like that. And then this is pretty much all the eyelid follow shader done. And you can see, if you look at this, you can sort of see why I wanted to offload everything to compute shaders and then instance it, because all these calculations up here are being done per vertex, even though they only need to be done per object, per each eye's position, instead of doing that on every single vertex. So yeah, we could optimize this a lot by just calculating our axis and theta in compute shaders per eye instance, essentially. Before I start offloading everything to compute shaders, I will make the eyeball shader first, just the basic idea, concept for it. And to do that, I'm also going to make a custom eyeball model, just to make my life a little easier. I just want to make sure that my UVs are aligned in a certain way so that I don't have to do those calculations in a script later, because so what I'm going to do is just align this one of these vertices, either this one or this one, with the z-axis, our forward axis, like this. And we do that because if we look at the UV space in here, as this, as the the U, I guess, coordinate gets bigger from 0 to 1, it gets bigger in a circle like this. We're going to use that to sample our iris texture for the eye. Like this is basically polar coordinates. Yeah, we just want to shift around anything too much. If we just export a sphere like this, the UV is already set up how we want, and the object oriented how we want. So just clear history, freeze the transforms, and then export this or rename it as like an eyeball sphere. Oh yeah, I already have an eyeball sphere that I've exported. But yeah, you would just export this as an FBX or an OBJ, and then import it into your Unity scene. Eyeball sphere, import this, and then up in our eye object where we have the eyeball, we're just gonna add the eyeball sphere mesh, and now we will need a material for it. So, and a shader. So I'm going to create a new HDRP lit shadergraph, call it shader, eyeball animated. And I'll also create a material, eyeball. We'll set this to our eyeball material and then apply it to our eyeball. And then, so to rotate our eyeball, we're going to use the same, rotation matrix function and everything, except this one isn't going to have a per vertex fall off. It's just going to rotate the whole eyeball and then clamp it at 1.57 again. Or actually, let me I'm just going to copy and paste this rotation matrix from axis and angle function. So we have to type all that again. Grab that. And then everything, again, this everything is pretty much the same in both of these objects. So you can see why, we want to, again, offload this into a compute shader so we're not calculating this twice for both materials. We do not need this fall off part. I'm going to ignore this, but I am just going to grab all the calculations we did, copy and paste it into here. We're going to have to, again, create those variables. So the target position, go right here, and place it that vector 3. And then this float is our object rotation limit. Rotation limit, set it to 0.57. Place that float, and then just input those. And this should be, now we have the rotation matrix set up with the eye. So if we just get the vertice positions in object space and just transform them with this rotation matrix, we just multiply them and output that to our position. We will have to do that for the normals as well. Oops. Like that. We save. And now we just turn on the wireframe so we can see that error. Oh, and of course we're gonna have to update this variable every frame again as well. So back in our script, in our update target position script, let me rename this to Eyelid material, and I'll call one eyeball material, and then eyelid material. Just copy and paste this line of code, replace the material with the eyeball material. The variable name is the exact same, so this should work. Oh, yeah, right. So I need to set my materials again because I changed the variable names. There we go. So now we have the eyeball following the target and the eyelid following the target. And then technically this, concept for this is pretty much done. You would just add normal surface shading and stuff and whatever else you might want, color, normal map, etc. Same for the eyelid. Oh, I guess I should, right, I will implement the changing pupil size. So to do that, first I'll take my object space position. Again, I will normalize it, and I will take the dot product with not the forward vector, but its opposite, the vector pointing backwards, opposite of the forward vector. So it'll be the vector going this direction, coming out from the back, and that means that the front, where the pupil would be, would get -1, or aka a black mask, and then at the back it would be white. So we have that. I'll add some variables. We'll add a pupil size. We'll just subtract this value from the dot product, because remember, our pupil is in the whatever, the negative area, the negative range of our dot product. So we'll just, further subtract values from that. And then we'll also multiply everything by some, call it pupil edge hardness. Just to make sure that edge is, really crisp for the pupil. And then if we saturate that, let me set a default for this, like 50 for the hardness. And let me also group all these parameters for now. Eyeball rotation. So we have the eyeball material, we have this pupil size. If we go, so at 0, it's actually basically, exactly halfway along the sphere. So if we go, into negatives, it'll get smaller. So like -0.99 is basically the smallest. We don't want to go beyond that, so we could clamp this pupil size value to something like the like our minimum -0.99. We can make the max something like -0.5 if we don't want it to get bigger than that. So if we look at this now, this is the biggest we can make our pupil for the eyeball. Oh yeah, and then we have the, of course, edge hardness. Yeah, we can just make this a very crisp edge if we want. What we want to do now is have as the pupil size increases, it sort of pushes the iris, like it, the iris gets squished, essentially. So we want to maintain a 0 to 1 range that just keeps getting, just the width of it keeps getting smaller and smaller, but it's still a 0 to 1 range. And so to do that, we're going to use the inverse lerp node. If you've never used this, it just instead of like a normal lerp where you input 0 to 1, the inverse lerp outputs a range of 0 to 1 based on these two input values. So if in these conditions, if our input is 0, we'll get an output of 0. If our input is 2, we'll get an output of 1, like that. So what we want to do is we want to take our pupil size. We're going to negate this, and then we'll input this into the B value of our inverse lerp. We'll just keep the A value at 0, and we take this subtraction, put that into the T value, like this. And then if we just saturate this and view it in our base color, it's kind of hard to see, but there's like a line here that isn't moving. It's very hard to tell like this, but there is a line right here that is staying exactly where it is. This line is the value 1, and then we're just changing, where the 0 point starts, essentially. It'll be easier to view if I, okay, so here we're also going to add another variable, which will be the iris size. Yeah, and if we just subtract it, or I guess it would make more sense if we add the iris size to this value and then pipe that into the B slot. Because, as if we get negatives, this value is a positive value incoming, so if we add negative values, as our iris value is getting smaller, then our offset, where the white value is. So kind of hard to explain, but you can see how that's pushing this value back and forth. The point where the gradient is 1 is just changing that position. So we make our iris size like negative 0.5 maybe. And then, as our pupil is changing size, it's squishing that range of values. And then we'll use this inverse lerp, this output to sample a texture. So we should add a texture 2D, which will be our iris texture, like that. Yeah, we just output that temporarily, and then I will set it to, oh, I don't have any textures, which means I will create a new folder called textures and import it. Okay, so here are the textures I've imported. They are like water normal maps, but for the purposes of this tutorial, they will work. But you should, actually create some good iris textures and everything. And then make sure, of course, your normal map is tagged as a normal map as well, because we will have a normal map for our iris texture. If we go back to the material, to our texture, and input this. This is where, the way we set up the UVs in Maya is going to help, because this X range is just basically a loop like this, the U value. So if we go back to Unity real quick, grab our UV, split up the red channel, which is our X channel, and we'll just make a vector 2 using the inverse lerp as the Y component, and the UV R component as our X components. Use that as our sample coordinates, UV coordinates for the texture. And yeah, now we have some semblance of a texture. You can see how the iris size is just, it's essentially tiling. Yeah. Once we actually, take our pupil and just, since this is a black and white mask, we can just multiply it with the texture here, and then output that. And now you can see how our pupil is just pushing the iris texture back. It's just squishing it as it gets bigger. We can also add a tiling value right here, coming out of, just multiply this value by some number, which means we'll add another variable that is our iris tiling. I'm going to default it to 10. Output that. Yeah, so now we can crank this up. As long as it's a whole number, it'll tile seamlessly like this. And then you can see this line right here where the texture ends, where that's basically not moving. Yeah, unless of course we change our iris size like that. Then of course we don't want this texture to tile forever. We want just like the white of the eye color to be back here. So to do that, we're going to take this inverse lerp, and we're going to do a 1 minus to invert the mask. And then here we're gonna, guess we don't want to use the pupil hardness. We also want to have another variable. We're gonna call this iris color fall off. This variable is just gonna control, how sharp this fall off is. That blends from the iris texture to just whatever is, the white of the eye behind it. Fall off. Let's play this together. We're gonna saturate this, and then here we should also. So we have the color or the the grayscale texture for our iris. We should also get the iris normal map. Let me grab that. Sample it using the same UV coordinates, and make sure it's set to a normal map. And then here I'm gonna swizzle out the XYZ components and lerp that together with just 0, 0, 1, like a straight tangent space normal direction. And we're going to use a combination of the pupil mask and the inverted iris mask. So when we take these two saturate nodes and multiply them together, it'll give us a mask that we can use to lerp our normals. So if we put this in our normal slot, grab our normal texture. Oh right, we have this fall off set to 0. We need it at least set to at least 1. You can see, this is how it's affecting our normal map right now. Let's set it to 3. I think that was a good number. We might have to increase the strength of this normal map, but you can see it is applied. Then what we want to do is just lerp, well, before we lerp this, we should multiply it with a color. That'll be our iris color. So we add a color parameter, call it iris color. Drag it over here, default it to something. And then we'll just take this and we'll lerp, we'll put it in our B slot, and we'll use the inverted inverse lerp as the T value between that and some eye color. So I guess we should get one more color and call it eye color. This is probably fine as a white. And then multiply this by the pupil mask. And I'll put that in our color. And so now we have the eye, pretty much, I suppose. Let me my smoothness at 1. I guess you could also create a parameter for smoothness as well. Smoothness. But you probably always want eye smoothness to be at 1, but we'll make a parameter anyway. Let me just make it a slider, 0 to 1 range. Okay. So yeah, now we have a very nice glistening eyeball. You can change the iris size like this, as well as the pupil size, which will, squish that iris down when it dilates, when it gets bigger. If we had a better texture for the iris, this would look a lot better, but it is what it is. Yeah, it looks a lot better, when it's like sort of stretched out like this. But yeah, so that's that. And then of course, this all follows our Alright. Whoops. So yeah, I'm just grabbing object space. I'm not getting our updated object space. So what we should do is add a block node and a custom interpolator. This is just, an interpolator will pass data from the vertex vertex part of the shader to be accessed in the fragment part. And if we need our updated object positions, we should grab, sorry, not object, but updated vertice positions, that we should grab those, put them in this custom interpolator. We'll rename this to position object space underscore OS, as well as set it to a vector 3. And then to access it, we'll get the custom interpolator from right here. We just type in custom. There's a custom interpolator tab. We can grab our position object space. Put it right there. Save. And now. Okay, yeah. So we actually need the unmodified object space vertices, because since we're using the dot product, yeah, we don't want them to move. We want them in their original state, as if there's no transforms applied to this eyeball. So yeah, we need to pass the unmodified object position vertice positions. Let me rename this. Unmodified position object space to be more clear. And save that. And now everything will follow our object around properly. And now, of course, we, this is a little messy, but yeah, now we should definitely create some categories for these parameters. So we create a category called, iris parameters, iris color falloff, iris texture, iris size. maybe one more category for pupil parameters, pupil edge hardness, pupil size. Then I suppose usually I also create a category that I just call hidden, just for variables like the target position that are getting updated through script. Just keep them separated in a category at the bottom of the shader. I'm also going to go back to my eyelid shader real quick. I did forget to add the blinking, and I'm just going to add a normal map and a color just to make it look a little better. So first for the blinking, usually I would, generally I would grab the instance ID, but I've been having a lot of trouble like using, the default GPU instancing options. This never seems to work for me. I can never access my instance ID by activating this. I don't know if you're even supposed to be able to. Maybe you are, maybe you aren't. Eventually I will, we will add custom functions that will turn on our instancing ID. I assume that's how you're supposed to activate it or enable it. But before we do that, go to the eyelid. I'm just gonna add a few nodes that'll just, make the eyelid blink every now and then. Again, this stuff will later be, again, calculated in a compute shader for efficiency. But for now, I'm gonna get the object position. I'm just gonna split and add all the components together just to get like a random offset kind of like this, and then multiply it by something like, I don't know, 200, maybe 100. Actually, we'll do like 400. And then we'll get our time variable. We'll multiply this by some factor. So let me do a eyelid blink, or actually let's do blink speed. Put this on 10 as default. Multiply that with time. Then we will add that to our offset. We'll take this value. Jeez, don't look at that. I guess we can create another float. We'll call this blink frequency. For now, I'll put it on 100. And we'll just mod this increasing value by our blink frequency. So now we have a value that's going from 0 to 100, and then back down to 0, increasing to 100, like a sawtooth wave kind of. If we subtract, or rather, if we take a constant, pi in this case, and subtract this mod value. When this mod value is 0, the subtraction will output pi. When it returns pi, this output will return 0. So what we'll do is we'll take the max between this value and 0, which is essentially just clamping it above 0, making sure it doesn't go negative. And then if we take the sine of this, it'll return a value that's, you just saw it blink once, but 0, 1, like, yeah, just an oscillation of 0 to 1 to 0 very fast. And then if we do a 1 minus on this and multiply it with our eyelid rotation variable, then we'll get, a blinking eye that blinks every however many, based on our blink frequency. So turn this down to like 30 for now, maybe. Oh right, I don't have animated materials turned on. Okay, there we go. So yeah, this blink speed, this is what we're multiplying time by. So you know, as we increase that, the blink will get faster. Maybe 15 is good. Then we can change the frequency, you know, just how often it blinks. And since we're using the world position of the object, you know, it's kind of different for every object. This can obviously be more complex, but yeah, these are, oops, this is a lot of calculations per vertex that again, we could just be doing per object. So we could vastly reduce the amount of calculations we're doing if we did this in a compute shader. But yeah, let me also add a eye normal map. And just sample that with the default UV coordinates. We can also add an eyelid color as well. Okay, now I think it's probably time to start transferring everything over to scripts and compute shaders to optimize stuff. So my scripts folder, I'm going to create a C# script. I'm going to call it Eye Manager. And this is just going to be in charge of like keeping track of the number of eyes in the scene and dispatching the compute shader and drawing and instancing the meshes. Then I'm also going to create a game object that I'll call Eye Manager. And you can put all your eye objects underneath the Eye Manager like that if you want. Let me also drag this script onto there. Okay. And so we want the Eye Manager to keep track of the, you know, all the eyes in our scene, the eye objects. And then we want to be able to access them pretty easily. So you could either ensure that the eye transforms or the eye objects, game objects, are always like children of the Eye Manager game object, so we can just access the children very easily and get, you know, the number of eyes if we're, of course, hand placing the eyes in our scene. We can also add another script to our eyes, like a, you know, an eye script that'll then tell the Eye Manager, update a list in the Eye Manager that will, yeah, just populate a list in the Eye Manager whenever an eye is active or inactive. It'll add or remove itself from the list. I think that's a pretty good way to do it, so I'm going to create another script, and I'm just going to call it eye, and this is just going to go on all of our eye objects, so drag that, open that, delete everything for now, and so I'm going to go back to my Eye Manager class, and I'm just going to create, you know, the very first thing I'm going to do is create a public static list of type eye, like this, and I'll call it eye list. Like that. So now we have, you know, a static list on our Eye Manager, and then from our eye, you know, class script, if we use our on enable and on disable methods, we can access the Eye Manager eye list and just add, you know, this eye object to it on the enable method, and then on the disable we would do the opposite. We would remove it from the list. So we would do Eye Manager dot eye list dot remove, and then this, you know, the object this eye script is attached to, like that. And now we have, you know, if we are creating eyes in the scene that have this script attached, then they will add themselves to this list of eye objects. So yeah, it's a pretty easy way to access them all. And then, so since we're going to be using this script to, instance and draw, we're going to be calling draw mesh instance indirect from this script. That means we'll need, an eyelid mesh, an eyeball mesh, and the corresponding materials for them. So I'm just going to add a serialized field, and then declare our two meshes. So we have the eyeball mesh, or the eyelid mesh, and the eyeball mesh. And then we'll also have two materials for these. So we have the eyelid material and the eyeball material, like that. I guess we could also add, so we should probably add two more parameters, just the compute shader that we'll be executing eventually. So private compute shader, compute shader. And we'll add for now we'll add a private transform, which is our look at object. I guess this look at transform, eventually we'll probably want this as you'll probably want this as a public transform instead of private, so that we can just set it from outside the script, from just wherever we want our, actually I'll just make it public. Might as well make it public for now. But yeah, we might want to set this transform just from outside the script, from whatever object we want our eyes to look at. However you want to do that. And so those are all our visible variables that we want, visible in the inspector. And now, in order to, draw many instances of something with, instancing, we want to store all the information for, each instance in a buffer. The idea is that we have two buffers. One is a static buffer that, is fully populated with every, all the data for each eye in the scene, whether it's being drawn or not, whether it's in culling range or not. So that would be stuff like the object to world matrix, the world to object matrix, any rotation data that we want, any blink data that we want. That's all going to be stored in one sort of static buffer. And then we're going to declare another buffer, a dynamic buffer, that will update its count and populate itself with new data every frame, with the compute shader. It's called an append buffer, if you were curious, and in a compute shader we'll pass in an append buffer. And every frame we reset its count to 0 and then append any eye object that is visible in the frustum or whatever in our culling, or any eye object that won't be culled, it gets appended to the dynamic buffer, and then it gets drawn with mesh instancing. So let me declare a few compute buffers. So like I said, we need one static buffer, and then we need a dynamic buffer, and that should do for now. And like I said, so these buffers, they need to store some form of our eye data, which would be the transform matrices, rotation data, and other stuff like blink data. So what I'm going to do is create a struct that has all that data just contained within the struct. You can call it buffer data. And then what we'll want is a matrix 4x4, which is our transform matrix, or we could also call this the object to world matrix. I'm just going to call it transform matrix though, because it has all our transform data to get our eye from object space to world space. as well as an inverse transform matrix, which would just be our world to object space transformation. And we need this because, if we look back at our shader, we're transforming the the new forward vector, the vector from our eye to our target object. We're transforming that back into object space before we do these calculations. So we do need to pass in the inverse matrix in our compute shader, into our compute shader. And then I'm also going to declare a vector 4. I'll call this one rotation data. This is just going to hold the axis of rotation and the theta values. You can say x, y, z. It's our axis, and z or w is our theta value. And then for the eyeball itself, we need a 3x3 rotation matrix. There's no matrix 3x3 in C# by default, or Unity structures by default. We could make a matrix 3x3 struct, or you could just pass in 3 vector 3s, which is what I did, and then call them rotation data in the X, and then we'll do it in the we'll add 2 more for Y and Z as well. And then we'll also have a final float that is our blink value. Each eye object will have its own blink offset and everything. So now that we have our struct and our buffers, we can initialize those buffers on play on our start method. And I'm going to create a method for that called initialize buffers. And what it's going to do is just create our compute buffers and set any initial data that they need. And in order to get our buffer size, the size of these buffers would be the number of eyes in our eye list. Actually, here let me declare two more private int variables. One is going to be the buffer size, and I'm going to create another one called thread groups x, which will be used for our compute shader when we dispatch it. I'm going to go ahead and declare that right now though. And so for our buffer size, we want to get the count of eyes in our eye list. So we'll just use eyelist.count. So that gets our buffer size, and then now we can actually initialize our static and dynamic buffers. So we'll create a new compute buffer for our static buffer. Here the count, is just the number of elements in the buffer. So we'll pass in the buffer size, and then the stride is the size of the data of each element in the buffer, and we're passing in this buffer data. So we know that a float has a size of 4 bytes. So if you just look at how many floats are in this, we have 16 in the first matrix, 16 in the second matrix. We have 4 in this vector 4, 3 in this vector 3, etc., etc., and then 1 float in this. Yeah, so you can basically just count the number of floats. So we have 16, 32, 36, 39, 42, 45, 46. So if we did size of float times 46, that'll get us, our buffer size. So we have the static buffer initialized, and then we also set the dynamic buffer to a new compute buffer, again with our buffer size. The same size per element. And then here we'll also need to set the compute buffer type, and this is going to be an append buffer because we're going to be, again, appending values to it, or appending the elements, I guess, of the buffer to it within a compute shader. So yeah, got that. And then I'll go ahead and also set this, I will set the counter value after I initialize it to 0, just to make sure that we're starting, at 0. And we're gonna, be resetting the counter value every frame. Because that tells the draw mesh instance in direct how many instances to draw based on that counter value. And then I actually did have one more buffer, a blink offset buffer that I was sampling in the compute shader. I didn't add this as part of the struct because it's not getting, we don't need to read from the blink offset in our material, but we do need a blink offset per object. So I'm just going to create a blink offset buffer as well. It's just going to be basically an array of floats. So all I'll do is just blink offset buffer, set that equal to a new compute buffer of our buffer size, that is the size of a float, like that. And so now we need to actually populate our static buffer with, the initial eye position data and everything. So I'm gonna declare an array type of buffer data, call it buffer data, and its size will be, our buffer size variable, like that. And then I guess we can also declare our blink offset buffer. So call this blink offset data. Also set this to the buffer size. And now we need to just iterate through our eye list and add the necessary matrices to our buffer data array list. So can I do a, yeah, there we go. So while I is less than the eye list dot count, or I guess we could actually just do buffer size here since we have it. We will increment I, and so in our buffer data array, we'll grab the current index, and we'll set each transformation matrix to the transformation matrix of the current eye that we're iterating over in the eye list. So if we get the transform matrix, we'll set that equal to the eye list dot, so the corresponding element in the eye list, its transform, and then to get our transformation matrix, which is transforming from object to world space, we get this local to world matrix. And then we'll also do the same thing for the inverse transform matrix. So we'll grab the corresponding matrix, which is this world to local matrix. Grab this, set that equal to the inverse transform matrix in our buffer for this element. And then I'll also just set some default rotation data for our rotations and our rotation matrix. This will just be a vector 4 with just like a forward vector essentially, like that. And then I'm not actually sure if we need to initialize these, but I just like doing it for peace of mind. I'll just set the I'll set our, each of these vector 3s is a row and a matrix, but I'll just set them to the, I'll just set them to vector 3s dot 0, vector 3 dot 0s, like that. For the X, Y, and Z components. And then we'll also set the blink offset data. So here, what I did, it's pretty simple. I just used, well, all we do is just get a random value using the random class. This just returns a value in the range of 0 to 1. And then what I did was multiply it by some value. So that would be, a blink randomness value, which is just increasing how much those offsets are. So if we come up here and add a new property, I'll just add a float that is called blink. Blink offset. Blink randomness, I guess works. Let me default this to like 500. And then all we'll do is just multiply this random value with our blink randomness, like that. And then I'm also going to floor this value, just to make it a little easier to work with, so it's a little bit more predictable in our compute shader. And so this is our, eye data buffers initialized. Everything should be good to go here. Well, not quite. The last thing we have to do is actually set the data from these arrays into the buffers themselves. So we just need to do static buffer dot set data, and then we'll set the, we'll just set the data from this buffer data array that we populated. And we'll do the same for the blink offset buffer. Just set the data equal to the blink offset data array, like that. And so now that we've populated our buffer data and everything, then we need to pass these in as parameters to our compute shader. So, and as well as our materials, or our material shaders. So if we create, a method called something like set shader parameters, within this method we'll just set the we'll set parameters that are contain this buffer data. And of course this also means we'll need some, we'll want to get the name ID, the int name ID from the strings, because we don't want to be recalculating the name ID every frame. So if we go up here, I'll create a private read-only int. So what do we need to pass in? We need to pass in the, so to our compute shader, we need to pass in all 3 buffers as parameters. So we'll get we'll create a variable called static buffer ID, which would be our, we call this shader.property2id method. And then whatever your static buffer ID is, in this case I'm going to make it underscore static buffer. So now we have this static buffer ID, and we'll do the same for the dynamic buffer and the blink offset. So if you want to make this look nice, we can put this down a tab and then create our dynamic buffer ID. This is just going to be underscore dynamic buffer. And then we'll also create our blink offset buffer ID, which will be equal to underscore blink offset buffer. I guess it's Visual Studio, they have this, these region modifiers. Whoops. So this is kind of nice. We just collapse that if we ever needed to, all our properties, because we're going to be adding, quite a few more eventually. So yeah, this is I'll just keep our properties at this for now, and then back in our set shader parameters, we're gonna, again, our compute shader is gonna need to receive all these buffers, and our materials only need our dynamic buffer. First, we're gonna take our compute shader and set a buffer parameter. Maybe it's better to actually create the compute shader now. Might be, for the sake of clarity, that might be a little better to do. Back to the project. So in my assets shaders folder, I'm just gonna create another folder called compute shaders. And then in here, I'm gonna create a compute shader, and I'll call it calculate eye data, maybe. Okay. Then we can open that. Okay. If you've never used a compute shader, I'm probably gonna be bad at explaining this, but yeah, everything, obviously everything's running in parallel, so everything gets its own unique thread ID, and this number of threads identifier up here with an 8.1, this is just specifying, the dimensions of the group of threads we're going to be using. And thread groups are generally, I believe, on NVIDIA GPUs, I think they're in groups of 32. In AMD, it's like 64 or something. So, you can see this thread group is it's 8 by 8 by 1, which means it's, 8 times 8, 64 times 1. So a group of 64 threads. If this was 2, it would be a group of 128. And it's, sometimes it's useful to use both your the X and Y thread groups when you're, writing to something like a texture, which is a 2D, the ID corresponds nicely to the 2D texture space. But for our purposes, since we're just writing to, buffers, all we need is like a thread group like this, or thread sizes like this, just 32, 1, and 1, just, a one-dimensional thread group. And then, so if we go back to our eye manager, and actually let me then write out our parameters. So, above the thread group, we're just underneath the pragma. Oh yeah, this pragma, just we could have a bunch of these if we have, multiple kernels. This is the kernel, that we're going to be executing from our script. If we wanted multiple kernels, we could just write pragma kernel something like this. And then of course we would define it down here with, the number of threads, that, and then, just pass in our uint ID, like that. And so yeah, so now we have, 2 kernels that we can execute based on a kernel ID. This one corresponds to 0, and this one corresponds to 1. And there are also methods within script where we could, grab the kernel based on its name instead of just using 0 or the int index of it. But yeah, I only need 1 kernel for this, so delete that. And we were passing in buffers as parameters for, our compute shader, which means this underscore identifier name is what we're gonna, declare in the compute shader. So like this, we'd have a, our static buffer variable name would look like this. And since our buffers are holding, this struct, this buffer data struct, we're also we need to duplicate this into our compute shader. So declare the struct that is buffer data. It has a transform matrix, an inverse transform matrix. It has the rotation data. We have the rotation matrix X, the rotation matrix Y, and the rotation matrix Z, and then our float, what was it? Blink. Oh, it's just blink. Okay. So yeah, so now we just have the exact same buffer structure, or buffer data structure in our script and in our compute shader. And so now we can, actually declare the buffers themselves, and these will be structured buffers like that. And then we'll declare the type. So, well, there's a few types of buffers. We have structured buffers, we have read-write structured buffers, which is what we're going to be using. And then we also have append buffers, or what is it? It's append. Oh, append structured buffer, like that. For our static buffer, we're going to use the read-write structured buffer because we need to read that data. And it's going to be of type buffer data. And then we'll use, the underscore identifier name, underscore static buffer. Set that. We have a dynamic buffer. This is the one we're going to be appending values to. So in this append structured buffer, this will also be a type buffer data. And its name will be the underscore dynamic buffer. And then we also have the blink data buffer that we're passing in, the blink offset buffer, which is just, just a buffer of an array of floats essentially. So declare that, blink offset buffer like that. And now we can access, each element in these buffers using the dispatch thread ID in our kernel. But of course, before we can access them, we have to actually pass them into the compute shader. We only need to do this once. So I will take our compute shader and I will set a buffer parameter. Our kernel index is 0 because we only have the one kernel in this compute shader. So yeah, we have that. We have the buffer index. We have the name ID. So this will be, the static buffer ID. Then we'll pass in the static buffer like that. We'll do the same for the dynamic buffer. So kernel index, dynamic buffer ID, dynamic buffer. And we'll also do the same for the blink offset buffer. Like that. And then for our materials, we're only reading from this dynamic buffer in the material. We don't need the blink offset buffer or the static buffer to be passed to our materials. So we'll just take our eyelid material and set buffer using the same name ID, so dynamic buffer ID, and pass in the dynamic buffer. And we'll do the same thing for our eyeball material. Like that. And eventually we will be setting, additional parameters that are just, basically uniform values. It would be things like, we'll pass in the rotation limit, we'll pass in the actually we won't pass in the follow strength because that's per vertex, but we will pass in a blink frequency, a blink speed, yeah, for our eyelid. And then for the eyeball, you know, it'll also read the, well, it's the same compute shader, so same variable there. Yeah. So the first thing we're gonna do in our compute shader is access the data from our static buffer. Since we have a 1D, you know, our thread groups are like one-dimensional, we can just, all we need is the X component of our dispatch thread ID. So we can declare a uint, just a regular, you know, one-dimensional uint called TID, thread ID, and set that equal to the ID.x to make things easier for us. And then we'll create a buffer data struct or object called buffer data that is just, you know, the data of our static buffer at the current ID. Like that. And then what we want to do is, you know, take that, you know, the transform data and stuff and calculate, you know, output the rotation data, this rotation, these rotation matrix values and this blink value, like that. And so to do that, you know, we need our target object position. So I'm going to declare a few more variables, a float3 underscore target position. And then what I'm going to do is come up above our thread or above our kernel and create a method that will just calculate, you know, it'll calculate all our rotation data. And it's just going to be doing, you know, exactly what we did in the shader. We're just transferring all these nodes into code in our compute shader. So if we have a void, calculate rotation data method, we'll pass in the position of, you know, the current eye object. So we'll have a float3 position, and then we want to write this to our buffer data. So I'm gonna declare this as an in-out. This is an input and output. We'll call it buffer data. Buffer data, like that. Because, you know, we want to be writing to the dot rotation data of the current element in our buffer. So first I'm gonna just define our forward vector, you know, the z-axis vector, which is just a float3 with 1 and a z. And then we're going to get our target vector, which is so it would be, you know, we grab our look at position, or our target position, excuse me, and subtract our position from that. That gives us the vector that is, you know, the vector from the object to the target. But this is not in object space, this is in world space. So we need to transform this with the current inverse transform matrix to get it back to object space. So we're gonna, you know, use the inverse matrix, the current inverse matrix that we're passing in. That's our, you know, buffer data. We're gonna transform this position. So when you want to multiply something by a matrix in, you know, like shader code, we use the mul function, and then we pass in our matrix, which is our buffer data dot inverse transform matrix, and then, you know, we have the vector 3 target, you know, the target vector direction. But we want to make this a vector 4 because, again, we're multiplying by a 4x4 matrix. So I'm just gonna create a float 4 that is, you know, our target vector, and then I'll put 0 as the last element. Usually when you're transforming or actually not usually, but when you are transforming directions and vectors, we use if it's a float 3, you would usually transform it by putting you would put 0 as the last element, and if it's a position, then we would put 1 as the last element in the float 4. Since this is just a direction vector, I'm putting 0, and then since we only need float 3 out, I'm just going to grab the x, y, and z components. So just append dot xyz to the end, and then I will normalize that transformed vector like that. So now we have our 2 normalized vectors, which means we can take the cross product and set our rotation data axis from that. So if we grab the buffer data dot rotation data dot xyz, this is going to be our rotation axis, or what stores our rotation axis. We'll take the cross product between the target and our forward vector, like that. Forward. And then we also need to normalize this. So just wrap that in the normalize function, like that, or normalize method. And now we need the theta value, which is going to be the W component. So first let me declare just a float W. And what I'm going to do is, you remember we have the fast Arc Cosine function that we made in our shader helper methods. So we can literally just copy and paste this pretty much exactly as it is into our compute shader. We just remove this underscore float from it. So above the calculate rotation data, I'm going to have the fast Arc Cosine function. It's not going to be of type void. I'm going to have it return a float, and then we'll just add return theta at the end here. Oh, I should also declare that as a float, like that. So this float W, first we need to get the dot product between our target and our forward vector. And then we just, use our fast arc cosine function on W, so it's now in a range of 0 to pi. Remember we negated it in our in our material function, or in our material shader graph. So we're also going to negate it in the compute shader. So just multiply it by -1 to get the rotation going in the proper direction. And then since we were we implemented our we had a rotation limit that we're clamping between. We want to do the same in the compute shader, which means we need another parameter. So I'll just declare a float I rotation limit, and then of course we also need to pass this into the compute shader from our iManager script. So up here where we have blink randomness, I'm just going to add a float that is an I rotation limit. And I'll default this to like 1.57, which is half of pi. I'll keep it as a parameter because we might want to change it. But yeah, so now we have that variable. We'll come down to our region where we're declaring our property IDs, and I'll create an I rotation limit ID, which will be our I rotation limit underscore I rotation limit. And then we'll go back down to our set shader parameters method, and we'll set the float in the compute shader. Like that. So we have our I rotation limit. Before we negate this, we'll just take the minimum of W and our eye rotation limit, like that. And then finally we can set our rotation data .W equal to the W that we just calculated, our theta value. Since our, so this is, the data that's going to be passed into our eyelid shader to construct, because we are still going to construct our rotation matrix for the eyelid per vertex in the vertex shader. But for the eyeball, since each vertex is getting the same influence across the whole eyeball, we don't need to calculate this in the vertex shader, so we can calculate the rotation matrix in the compute shader. But it uses some of these variables, so I'm just going to create one more method that is a void method, and it's going to be called rotation matrix components, because again, we have our rotation matrix stored as 3 float 3 components. So rotation matrix components from axis and angle, and then pass in the axis, or actually pass in theta, then the axis, and then we'll declare out keywords here, and we'll output the float 3 rotation matrix x value. I'll just keep it as an x. The float 3 y, and the output float 3 z, like that. And if you remember, we have the same method in our shader helper methods .HLSL file. So again, I'm gonna copy and paste that. So everything within the body of the function, I'm just gonna, because we're doing the exact same thing, I'm just gonna paste that in. Oh yeah, we have our axis defined as A, so I'll make the axis A. And then we're not actually, I will modify it a little bit, because remember, we're storing everything as vector 3s or float 3s, so we don't need to declare this matrix anymore. So we have, these are like essentially our 3 x, y, and z vectors. So what we do is we just set x equal to the first 3 values of our matrix, set y equal to the next 3 values, and we set z equal to the last 3 values, like that. And so yeah, we want to store these 3 values in these rotation matrix x, rotation matrix y, and rotation matrix z variables. So when we call this rotation matrix components from axis and angle function, first we'll pass in this w value that we just calculated, which is theta. Pass in the axis, which is our buffer data.rotation data.xyz that we calculated. And then what we want to do is, store that data in these components. So we'll pass in the buffer data.rotation matrix x, the rotation matrix y, and the rotation matrix z, like that. And so now those 3 vectors are getting stored in this in our corresponding buffer data element. Also back in the compute shader, I guess I need to add float 3, data structured in front of the values before we set it. I don't know why I didn't do that. Then of course we actually need to still need to call the calculate rotation data method from our kernel. So calculate rotation data. We need a position. So we can get our position data from our transform matrix, just the local to world one. So if we declare float3 position, this will be equal to the buffer data dot transform matrix. And here we'll get the actually, so we need to grab the fourth column, and to grab the first three elements of the fourth column in the matrix, which store our, that's where our transformation data is stored, or our transform data, or our, position data is stored. So we want the first row, the index for the first row, and then we want the third column, like that. So that would be our first element. Let me also wrap this in a float3. So that's our first element of our position. Our second element is in the first row. So we're just moving down the rows and grabbing the fourth column, not the third column, the fourth column, index 3. And then third row, fourth column for our last element, like that. Yeah, so this is our float3 position that we grab from our matrix. So now we'll pass that into the calculate rotation data method. And we'll also pass in the current buffer data structure. And then that's all our rotation data calculated that we need to pass into our material. So we can save that. And now we want to calculate this blink value. So to calculate our blinking, we need a couple more parameters. We need a, if you remember from our shader or our shader graph, we had a blink frequency and a blink speed. In our compute shader, we're just gonna declare a blink speed variable and a blink frequency. Or actually, I'm gonna call this blink time, because we're gonna multiply time with speed in the iManager script and then pass it in as one variable like that. So back in our iManager, go ahead and write out the blink speed. Default it to 10 or 15. And then we also had a blink frequency. And I will default this to 100. Like that. And then down where we set our shader parameters, we'll again in the compute shader set a float. Oh, and we do need to calculate the ID for that. So our blink time ID is called blink time in the compute shader. Shader.property to ID. We have a blink time. Oops. And then we also have the blink frequency. So the blink frequency. Then we'll go ahead and set the blink frequency in our compute shader, like that. And then we need to set the blink time. And so to calculate our blink time, we're just gonna take our blink speed and multiply it with time. I guess you could use, there's a few ways you could get time, I'm just grabbing it from the shader.get global float, and we're gonna get our global, or actually, time is stored as the global shader time is stored as a vector 4, so we're actually gonna get a global vector. And the name ID, we don't want to use a string, but the name ID is just underscore uppercase time, like that. Oh yeah, and we only need the, so I believe the x component of the global time vector is like time divided by 2 or something, or like 10. The y component is just normal time, and then I think z and w are like sped up versions of it. Not 100% sure, but I'm gonna use time.y. Grab that. But remember, we don't want to convert this string, or we don't want this string to have to convert every frame. So back up in our ID region, then I'm gonna declare one more ID. I'm just gonna call it time ID. So that equal to the shader.property to ID underscore capital T time. Like that. And then instead of writing the string for underscore time, we just use our time ID. Like that. So now these values are getting passed into our compute shader. And blink time is something that will, obviously we do want to update that every frame. So eventually I'll be moving this line of code to a method that is update shader parameters, and I'll just put all the parameters that need to get, updated every frame, which would be this blink time ID, our target position. Did I even declare that? I haven't declared that yet. We will do that eventually in a sec. Actually, no. So before I forget, so this float 3 target position that we're using down here, we should not forget to pass that in. So before I forget, I'm gonna use compute shader.set vector. We need to calculate the name ID again. So that will be, maybe we want that. We want that to be the target position. I'm gonna call this target position. I don't know why I called it look at transform. I'm gonna make that target position. I'm gonna write out target position ID equals shader.property to ID underscore target position. So I will set that vector in our compute shader. All right, this is a transform. We just need to get the position. So target position dot position. And these two parameters are going to be updated every frame. So I'll make a separate method for them in a sec, and a separate method that's going to be updating every frame that we call from our update method. So back in our compute shader, we want to calculate our blink value for our eye. So we will make another method that'll just return a float. So float calculate blink. I'm going to pass in the thread ID as a parameter into this function for this method. And so first what we'll do is just initialize a float called blink, which will grab our blink time. So this is just a value that is increasing forever, essentially. And then we'll add to that the value from our blink offset buffer. And this is why we need the thread ID. We'll just sample it using the TID. And then we will mod all that by the blink frequency. Then, remember in the shader, when we were calculating the blink, we just, so we subtract from pi, we subtract that mod value from pi, and then take the maximum between that and 0. Up here, I'm going to define the pi constant, which is this. You can just, Google it or whatever, or type it in on your calculator and then just copy the value in. So we have pi, and then we want two references. So we subtract that value from pi. So blink equals pi minus the blink value. And then we want to clamp it, above 0. So we take the max with that value at 0. So blink equals max blink and 0. And then we'll take the sign of that, blink, and then we'll do a 1 minus to invert it. And then of course we also want to set the value in our oh wait, right, we're actually returning a float, so then we just return our blink. And then back in our kernel method, we just calculate blink, or take our buffer data dot blink and set that equal to calculate blink and pass in our thread ID. Okay, now what we need to do is we need to implement some form of culling, frustum culling as well as distance culling. Because since we're going to be drawing everything, manually, or we're going to be passing everything to the draw mesh instanced indirect method, we need to handle culling ourselves. And we can do that in the compute shader. So before we even calculate any of this data, we can make sure that the object is actually in view. And so to do that, first I'll just create a method that is going to be our boolean is, I don't know, boolean in view, I suppose you could call it. I'm going to pass in my the object position, the eye position, as well as the clip space position of the object. We're doing this so we can, test the position relative to our camera, so the world position. And we also want the clip space position to test whether it's in the view frustum or not. And yeah, I was referencing, when I was making this compute shader, I was referencing some of Ace Rolla on YouTube. He had a good series on how he's how he optimized the grass shader. So I was referencing some of his videos. They're pretty good. But yeah, I was just implemented the way he calculated frustum culling for his grass, as well as distance culling. But what we have to do is transform our object position into clip space so we can test, determine if it's in our view frustum. And to do that, we need to multiply our position by the view projection matrix, the camera's view projection matrix. So we need to pass that in as a parameter to our compute shader. Declare another float 4x4 matrix called I'll just call it the camera VP view projection matrix. Camera VP matrix. Yeah, something like that. And then back in our eye manager, I'm gonna go ahead now and create the update shader parameters method. I'm gonna go ahead and move these, both of our target position and our blink time ID. I'm gonna move that into the update shader parameters method because these will be updated every frame. And then we will also need to set that, or get the ID for our camera VP variable. So I will create a camera VP ID, which is equal to shader.property.id, camera VP, like that. And then to calculate our, well, so we're going to set a matrix, which is going to be our view projection matrix. And to calculate this view projection matrix, we're going to take our camera dot main dot transform, or sorry, transform, or not transform, camera dot main dot projection matrix, and we're going to multiply that matrix with the main camera world to local matrix, the inverse transform matrix. And this will give us a view projection matrix that we can use to calculate the, whether our object is within the view frustum or not. Oh, well, and then, since we have the view projection matrix, we also need to take this point and our object position and convert it to clip space. So I will declare a float 4, which is our view space. And then this is going to be equal to the, the camera view projection matrix multiplying or transforming our position by the view projection matrix. Since this is a float 4, we need our position to be a float 4 vector. And since it's a position, we'll put 0 as the last, not 0, we'll put 1 as the fourth element in the float. And then also where we were calculating our rotation data, just make sure you swizzle out the XYZ components for the position. So now we have the view space position. To get clip space, we'll declare the clip space like this. And all we do is just divide the view space XYZ components by the negative W component of view space. So we grab view space.xyz divided by the negative view space.w, like that. If you want a better explanation on how this works, just look it up. I don't have faith in myself to explain it properly. And then we'll set the clip space.z equal to the negative view space.w. And so now that we have the clip space position, we can call this in-view method. So we'll do that in a sec, but so now we have this in-view method, and what we want to do is just test everything based on the test if a point is within the frustum, as well as if it's close enough to the camera. So I'll create a boolean called in-view, or in frustum rather. And what we need to do is just test each component of our clip space. We test whether or not it is less than or greater than some value. And for reference, the clip space, it will return values in the x and y, that is, or I think all three values are in the -2 to 2 range. So yeah, it'll return values from -2 to 2. But on your actual screen, the range is 1 to -1, or -1 to 1. So even if an object is, off screen, it still might be at the value, and have like a clip space x value of 1.5. If it's a pivot is off screen, but it might be scaled large enough to be visible on screen still, so we can test if the clip space is less than like -1.8 or even 1.9. and only then do we cull. Actually, I guess, is it in? It might just be. It might not be clamped to the -2 to 2 range. I'm probably wrong there. But yeah, imagine that -1 to 1 is your screen space, and then -2 to 2 is like twice your screen coordinates essentially. So if we test the clip space, if it's less than something like -1.5, I think was a decent value, then we can cull it. Or if the x value is greater than +1.5, so if it's off the right side of the screen, and we'll also do this for the y, clip space.y less than -1.5. Why am I using commas? Oops. This should be, we need to test or if it's less than -1.5 or greater than 1.5, or the y is less than -1.5, or the clip space y is greater than 1.5, or the clip space dot z is less than something like -0.1 maybe. Then this will return true or false if it's within that clip space. And we can declare we can define a value up here that's like our, I don't know, our frustum cull value, and I'll set that equal to 1.5, just so we don't have like too many magic numbers in this script or anything. So I'll replace these 1.5s with the frustum cull, like that. Also make this look a little better. Okay, and then this testing if the clip space.z is less than -0.1 is just testing if it's behind, if the object is behind the camera. And then we also need to test if the object is in the camera's within the camera's far clip plane. And so to do that, we of course need to access the camera's far clip plane. So I'm gonna have to declare one more float value, which is just the camera, or actually I should call it far clip plane. Like that. It's just a float value. It's usually defaulted to 1000 in Unity. But back in our eye manager, we'll of course pass that in to the shader as a property. So we have our far clip plane ID should be equal to the shader property to ID far clip plane, and then we only need to set this once. Set shader parameters. I mean, unless of course you're changing these things in settings, in which case you might have another a third method that can be called for parameters that are getting changed in like game settings or something. But for now, I'm just only gonna call it once at the very start using our start method. Set the float, which is our far clip plane ID, and that'll be equal to our camera main far clip plane. Then back in the compute shader, we grab the far clip plane variable, and we just test if the distance is less than, if the distance from this position to the camera is less than the far clip plane. So we do distance. Did I pass in our camera position? Oh, did not. So we will also need a float 3 camera position that is getting updated every frame. So back in the eye manager, add another unique ID, camera position ID. camera position, and then in our update shader parameters method, I'll set the vector, which is our camera position ID, using our camera.trend, camera.main.transform.position, and so we grab it from here. We get the distance between the camera position and the object position, and then we test if that is less than the far clip plane distance. So this is returning true if it's within the, if it's less than the far clip plane. And then for our output, we just multiply the two, the is frustum and the is range, or in range, excuse me, variables together, like that. And so now, when we call, so now, before we calculate our rotation data in blink value, we'll instead test if the object is actually in range. So we call our InView method using the position.xyz, as well as the clip space position. And then I'll just move these two method calls inside the if statement, like that. I forgot to add one thing right here. When we're testing our frustum culling, we also need to actually, if any of these are true, we output false. And if all of them, return false, so we're within our frustum, then we return true. And now the last thing we need to do in our compute shader is actually, now that we've calculated all that data, we need to actually push it into the dynamic buffer. So yeah, we just push the updated buffer data object into our dynamic buffer. So what we do is we just do the dynamic buffer dot append, and then we pass in the buffer data. That we, initialized up here to be our, the current data, or the data of the current thread ID in our static buffer. Like that. And so now I believe our, we're done doing everything we need to in the compute shader. So yeah, all these methods, technically good to go. We do need to, now we need to actually dispatch our compute shader from the iManager script. So what I'm going to do first is calculate this thread groups x variable using our buffer size. So we can do thread groups x. We can set that equal to the buffer size divided by 32. I'm using 32 because our the number of threads in the x dimension of our kernel is 32. So we divide the buffer size by 32. So if it's 32, we'll have one thread group in the x. We'll have one thread group. If the buffer size is 33, then we want two buffer groups. So what we need to do, or two thread groups, excuse me. So what we need to do is just take the, we want to use this ceil to int function that just ensures, if we have our buffer size is 1, then the thread groups x is, 1. If it's 32, it still returns 1, and if it's 33, it returns 2. That makes sense. And then what I'm going to do now is add another method that is called execute compute shader, just to make things clear. All it's going to do is just basically, we call this compute shader.dispatch method, pass in the kernel index, which is in our case 0. We only have one kernel. We have the thread groups that we just calculated. So thread groups X. And then we pass in 1 and 1 for the other two dimensions. And we will be executing this compute shader every frame as well. Now, what we need to do is we need to actually draw our meshes. So Unity has a few methods for instancing objects. I'm going to create a method first called just a void method that's draw meshes. From the graphics class, we have draw mesh now, draw mesh instanced, draw mesh instanced indirect, which is what we're going to be using. And we also have, draw mesh procedural. Don't want to use draw mesh instanced because I believe it can only draw like a max of 1023 instances, whereas draw mesh instance indirect can draw like way more. Not exactly sure how many, but it's a lot more. And we need to call this method twice, once for our eyelid and then a second time for our eyeball. So the first thing we need to input is our mesh. So we'll take our eyelid mesh, the submesh index. We don't have any submeshes, so we'll just use 0 for now. If we had submeshes, if our mesh had submeshes, we would, I think, call this method again, and then update the submesh index. Set it to 1 or whatever. We'll use our eyelid material for the material. The bounds, so the bounds for when you instance objects is like pretty much just a giant bounding box in your scene that encapsulates every single instance. When this bounding box is not visible to the camera, none of our if none of our instances are in our dynamic array, then I believe I'm assuming this method can be optimized to just not draw anything. It optimizes itself, like if the bounding box is not in view, then nothing will render for those instances. It can offload. It's probably optimized. It's probably optimized to render a lot better with it. So we're gonna, of course, we should probably calculate the bounds using our eye transforms from our eye list, the position data, as well as the scale of each eye. So what I'm going to do is just declare a private bounds, call it bounds. I'll set it equal to the center. I'm just going to center it on the origin. Most likely you would center this, you would like calculate an average position within all your instances, like get the average position between all the instances and have that as your center. I'm just going to keep it at 0 for now. And then the size is how big the bounding box needs to be to encapsulate all the instances. For now, I'll just use vector 3.1. And then in our initialized buffers, I'm going to update our size component of the bounds based on our object positions. So in order to update our bounds, we'll create a new method called update bounds. Actually, we'll want to pass in a couple of parameters. The first one would be object scale, which is going to be the scale of our current eye object that we're iterating over. And we'll also pass in a position, which is the position of the current eye that we're iterating over. And I'll go ahead and call this method. We'll get the eye, the current eye in the eye list. Get its scale, as well as the position. And pass those in as our parameters for update bounds. And then within this method, we're going to create a new bounds variable, which is called object bounds. We'll set this equal to the eyelid mesh bounds, depending on whatever objects you're trying to do this for. Like our eyelid just is bigger than the whole eye itself. Like there's no reason for me to do the eyeball mesh. But if you had multiple meshes, with as part of like an eye object or something else, some other object, then you do this twice. What amount to do twice for each object if one is not fully encapsulating the other. But yeah, I'll get the object bounds dot size, and I will set it to the object bounds dot size dot x times the object scale dot x, and I will do this for the y and z components as well. So that is scaled up our bounds, or the size of our bounds, and then we also want to set the center position, and we can just use the actually, can I just duplicate this? We'll just set it to our object position, and then all we need to do is get the bounds object for our instancing, for our draw mesh instanced and direct. So we'll get the bounds, and then we'll call the encapsulate method, and then we'll just pass in the object bounds that we calculated, like that, and that should update our bounds properly to include each eyeball. And so now that we have that calculated, we can pass in our bounds to the draw mesh instanced and direct. Yeah, and then here we need, so our what is this? The fifth parameter is another compute buffer, a buffer with args. This is just a buffer or I believe the type is uint. It's just a buffer of length 5 that we pass in, that just has contains info like the count, how many objects we want to render, and like mesh data pretty much. And we need 2 args buffers, one for the eyelid mesh and one for the eyeball mesh. And up here where we declared all our compute buffers, I'm going to add 2 more. The eyelid args buffer and the eyeball args buffer. And so to initialize these buffers, I'm gonna go to our initialize buffers method outside of the for loop, and I'll create a new uint array called args, and I'll just set it equal to just a bunch of zeros as default. Oh, why am I using floats? Like that. Now that we have this set, we want to grab the first index, and what we do is we set this equal to the eyelid mesh. The eyelid mesh's index count. and then we use the submesh that we want. So in our case, we only have one submesh, the main mesh. So we just set that equal to 0, and then we will also set the second value in the array equal to the buffer size as an integer. So we need to just cast this to a uint like that, and then we can leave the other 3 arguments in our args array as zeros. If you did have like submeshes on your mesh, you would use them like this. You would, our third element in the array would be the eyelid mesh, for example, dot, we'd get like the index start and stuff. But we can just leave it at 0 for now. Doesn't really matter for our case. If you want to learn more, just Google some of this stuff. I think people like Ace Rolla also went over this, if I'm not mistaken. I think he covered it a little bit. But yeah, you can also just look at Unity's documentation as well. And then I'm going to set the eyelid args buffer. Wait, what? Dot set data, and I'll use the args array that I just updated. So I've set the eyelid args buffer data, and now I will just update this same array again using the eyeball mesh data. So eyeball mesh dot index count, and then element 1 in the array will be the the buffer size again. Actually, I guess we don't even need to update that then, since our buffer sizes are the same. We can do eyeball mesh or eyeball args buffer dot set data args. And now back in our draw mesh instance and direct method, we will put that eyelid args buffer in. And at a minimum, we only need these 5 parameters passed into the function, but you can add like things like material property blocks and turn off shadow casting if you want. For the eyelids, I'll go ahead and turn off shadow casting. Just add these extra arguments. And then for the eyeball, we'll do the exact same thing pretty much. Grab the eyeball mesh, the submesh index, the eyeball material, the bounds that we calculated, and then we'll input the eyeball args buffer like that. I'm going to let my eyeball cast shadows. One thing I forgot to do is actually initialize these arg buffers for the eyelids and the eyeball. So up here where I'm just creating all my compute buffers, also gonna set this eyelid args buffer equal to a new compute buffer. It's only gonna have one element. It's just this array, which is a size of uint that times 5, because again this array has 5 elements in it, 5 unsigned integers, and then we do the compute buffer type dot indirect arguments like that. We'll do that for both our eyelid args buffer and our eyeball args buffer. And now, since we're using compute buffers, we of course need to release these. We don't want these to be eating up memory when they're not supposed to be and breaking everything. So if we call on disable, for each buffer we have, we'll test whether or not it's null. So, or if it's not null rather. So if our static buffer is not null, then we'll release it, as well as set it equal to null. And we will do this for all 5 buffers that we have. So just copy and paste this a few times. Now we'll set this one to the dynamic buffer. Grab our eye blink offset. Offset buffer. Look at the eyelid args buffer. Eyeball args buffer. Like that. Okay. So our onDisable method should be fine. And then we actually need to, call all these methods from our start and update functions. So for our start function, we need to call the initialize buffers. Call set shader parameters. Because we can call update shader parameters as well. Then we'll execute the compute shader. I did actually forget to do one thing here in our draw meshes method. Before we call this draw mesh instance indirect method, we need to copy the count from our dynamic buffer into our arg buffers. So what we do is we just call the compute buffer dot copy count. Copy, so copy the counter value of the append or consume buffer into another buffer. So we'll grab our dynamic buffer, copy into the eyelid args buffer. Oh, whoops. And then we also need the the offset bytes. So all we need to do is just get the size of a unsigned int. Yeah, because our args buffer is just 5 unsigned int values, essentially. And then we'll do the same thing for the eyeball args buffer. And then after we copy the count, we just need to make sure that we set the counter value in our dynamic buffer back to 0. And then actually we don't need those 2 methods in our start method, we'll put those in our update method. So every frame, we're going to be calling the update shader parameters method. We're going to be executing the compute shader, and we're also going to be drawing all the meshes like this. I believe our iManager class script should be good to go. Back in our inspector, I'm going to go ahead and set all these, public variables. So like, we put our compute shader, we get our target object transform, grab our eyelid mesh, get our eyeball mesh, get the eyelid material, eyeball material, And then these are just parameters we can change if we want. And actually back in our script, eye manager script, we can, for example, in this eye rotation limit, we can clamp it. Whoops. We can add a range modifier above it that's in the range 0 to pi. Okay. So now we have a slider for our rotation limit that is, clamped to pi. So now what we need to do is update our materials to actually use our, the data from our buffers. And this was the part where I was like, I really didn't it took me a while to figure out how to do this, but in order to enable instancing and for material from an HDRP or for a shader using HDRP Shadergraph, we'll need to create a custom function that is set to string, and you can call it something like enable instancing. But then what we need to do is add this pragma. So we type, pragma instancing underscore options. Then we type, space procedural, like that. And then here we have some function name that we're gonna call, that we're gonna, define ourselves in another HLSL include file. I called mine instance data setup, like that. And then this line of code basically has to execute, this pragma needs to be injected at the beginning of your shader. So in our case, since we're basically the first thing we do is sample the normal vectors in the object space position. We just need to pass these. We need to add inputs and outputs for these that we just pass them through this custom function node. So all I'm gonna do is add a vector3 input that's, vertex input, and a vector3 that is a vertex output. Also add a vector3 normal input and a normal output as well. I'm not sure if you need both of them, or if it'll, it might just activate if we only pass through one, but I did both just to be safe. And then so underneath, within the body, all we do is set our vertex output equal to our vertex input, and we set our normal output equal to our normal input, like that. And then, so right here, where we have these two, this position and this normal vector, we're gonna just pass these values through this function right here. So grab the position and the normal, and then output them into these, into the rest of our shader from the other side. And basically just calling this, just defining this pragma and calling this function just enables, all the keywords and stuff necessary for instancing to actually basically be enabled in our shader. But we do need to define this instance data setup method in a HLSL include file. So in our shader include folder, I'm going to just duplicate this shader helper methods.HLSL, and I'm going to rename it. I'm just going to name mine I instance data, I think, because along with defining that instance data setup function, we're also just going to define some functions in order to grab the data from our buffers. So if we open this, this is the same code as our shader helper method, so we're just going to delete all this. And then we're also going to change this define keyword. We're going to call it something, you can call it whatever you want to call it. I'm just going to call mine eye instance parameters or something. That. And then here is where we're going to add this function, which in our case I named instance data setup. So it's just a type void called instance data setup, takes no parameters, and we can actually just leave the body empty and our instancing will now work. We don't actually need to put anything down here. However, if we don't, we'll need to manually grab the transform matrices from our buffers using a custom function in Shadergraph, and then multiply our vertices by them in here. Or instead of doing that, we can what we can do is define a Unity object to world matrix, and we'll use Unity's own like object to world keyword, matrix keyword. So we'll grab the object to world matrix that the keyword that Unity uses. This is a keyword in Unity shaders for the object to world matrix. But currently, for this, for our eye objects, if we're instancing them, it's set to, it's just like, I guess, an identity matrix at, the origin of our scene. But we want to define the matrix with the same name, and then we will, set that matrix that we just defined equal to the corresponding matrix, transform matrix in our dynamic buffer that we're passing into this material. And we'll do this for both the, I guess we could do it for the inverse matrix, although I don't think we actually need the world to object matrix in our case, so I won't. But of course, to access our dynamic buffer, the buffer that we, this dynamic buffer that we're appending data to from our compute shader. And again, remember we already set the dynamic buffer for both eyelid and the eyeball materials. We set that buffer in our set shader parameters method, which is called, at the start of the, when the game starts or when the scene loads. And then, so go back to this. So in order to grab our buffer, all we have to do, remember it's just the same ID as before. It's still the underscore dynamic buffer, because that's what we defined it as up here. Our dynamic buffer ID is just underscore dynamic buffer. So we have the dynamic buffer. We can just define it as a structured buffer like this. And then we will need to define the struct again, the buffer data structure. If you go back to the compute shader, you can see we defined it right here. And since these are both using HLSL, we can just copy and paste this over directly like this. And then we set this structured buffer to type of data buffer, or buffer data, excuse me, like that. So now we can access our dynamic buffer per object instance. So in this case, we set this local to world matrix equal to the dynamic buffer at our instance ID, and the keyword for Unity's instance ID is Unity underscore instance ID, like this. And then we'll do dot transform matrix, because this is the name of our matrix up here. And, you know, I guess Unity can't tell that this, Unity doesn't know that this variable name exists, this instance ID exists yet. So you'll get errors if you save this, but what we can do is just do an if def, and then we'll type Unity procedural instancing enabled, and then underneath this we'll do the end if, like that. Just put that within the function here. And yeah, now this, you know, isn't going to throw an error just because it's wrapped in this if def, pretty much. And yeah, so now in our material, when we do this, our material will automatically transform, you know, when we output these, output our vertices and our normals into these outputs, Unity will automatically multiply them with the, you know, the proper transformation matrix to get them to world space and clip space, etc. And then to get the other data from our buffers, like the rotation data and this matrix data and the blink data and all that, we will, you know, basically do what we did in the shader helper methods. We'll just define functions like this with this same underscore float precision or half precision or fixed precision or whatever, and then access them the same way within the shader. So for example, in our eyelid shader, we want to access our vector 4 rotation data. So if we get a custom function like this, we'll use the file that we just made, the eye instance data HLSL file, and the name of our function will be, yes, we can name it like sample eye data buffer rotation data or something, sample eye buffer rotation data, something like that. But yeah, so we have that, and then if we go back into our eye instance data.HLSL, we will define that function as a void, type void. We'll add the underscore float suffix to that. So this will be, you know, a float 4 output. So we'll type out, the out keyword, float 4 rotation data. And then to get this, all we need to do is just grab rotation data, set it equal to the dynamic buffer, add our Unity underscore instance ID. Oh, and then dot rotation data like that to get this value, this float 4 out of there. And this will work. This will throw an error in the in your, you know, Unity editor, but if you hit play, everything will actually work. You know, we'll be able to grab this value even though Unity thinks this variable doesn't exist or it isn't declared. But what we can do is, you know, in Shadergraph, Unity has this instance ID node. So if we pass this in as a parameter to the function, and then cast it to an unsigned int, then we can, you know, avoid our editor throwing an error. So if we declare float and just call it instance ID like that, then when we sample this dynamic buffer, instead of using Unity underscore instance ID, we'll just whoops, use the instance ID variable that we just made, cast it to uint, like that. Because from Shadergraph we can only, as far as I'm aware, there's no integer input for whatever reason. So yeah, we'll create the instance ID input and plug in our instance ID. And we'll create the vector for output, which is our rotation data. So we save that. But yeah, so our rotation data. So remember the first three components are our axis, and the last value is our theta value. So I'll plug that in there, and then make a vector 3 with the other three components that we plug in for our axis. Oh, and then we will also, since our theta is per vertex again, before we plug in our theta value, we should multiply it with this fall off, and then input that to there. We can delete all this, because we don't need it anymore. So yeah, so this is only going to work in play mode now as well, because of how we, I'm not executing our compute shader and everything in the editor. You could if we're in the editor, then we can run some block of code that'll execute the compute shader and stuff, but I did not bother with that. I'm only gonna run it during play mode. So for the eyelid, we got our, we sampled our rotation data, and then we also need to sample our blink data. So we'll do the same thing. We'll create a custom function. We'll call it sample blink, or sample eye data buffer blink. Set it to our eye instance data, and then again we'll add the instance ID input, then we'll have the blink float value output. Instance ID, copy this function name, go to our instance data.HLSL, and we will define that function. With our inputs and outputs and the underscore precision modifier. And then we'll set the blink equal to the dynamic buffer, sampled our instance ID, and then we'll get the blink. Like that. And then this just replaces all these nodes up until this multiplication with the eyelid rotation. So that just plugs into there, and then all this gets deleted. And then this is so now our eyelid shader should be fixed. It should work with instancing now. Save this. Oh, and we do not actually need these the eyelid and eyeball objects anymore on these eye objects, so I'm actually just gonna delete these real fast. Let me go to my eye script real quick. I'm just gonna add an all draw gizmos method for visualization. So let me just add a gizmos.draw sphere. Center should be at this transform position, and the radius should be the scale of this object, like that. So I'm going to duplicate this a few times. Like that. Okay, yeah. So there we go. We have our instances, or at least our eyelids, as of now. You can see the eyeballs themselves are still just at the origin because we haven't called the, we haven't called this enable instancing function from our eyeball shader. So we can see that it's kind of weird in this view. If we have our target object, our eyelids are following that. So now we're just going to do the same thing for the eyeball shader. We'll grab the rotation matrix as well as pass these position and normal vectors through our enable instancing custom function. So I'm just gonna copy and paste this function into here, like that. And then we'll put our normals, our vertices through there. We also need to grab our rotation matrix, so create a custom function. We'll call it sample eye data buffer rotation matrix. Choose the eye instance data HLSL file. And so in our eye instance data.hlsl, we'll define that function. Sample eye data buffer rotation matrix. Precision is float. At our instance ID, we're going to output a float 3x3 matrix. Like that. So yeah, we'll create a float 3x3 matrix M. We'll set the first element of that equal to we get our dynamic buffer, sample it, sample the instance, and we'll grab our rotation matrix X. This is setting the first row of our 3x3 matrix. And then we'll do that for the second row and the third row. Just make sure we're grabbing the rotation matrix Y and Z like that. And then we'll set our rotation matrix equal to the matrix M that we just made. Then we'll add our inputs and outputs here. Instance ID and a matrix 3. Grab our instance ID here. And then we can, delete all these nodes right here. Instead, just use this rotation matrix, like this. I'm also gonna change, use this interpolator. I'm just gonna set it to the instance value. And now our eyeballs should be fixed. Should see our eyeballs get drawn. Okay, yeah, there we go. So now we have our target object. Everything is working properly. We have eyes are falling properly, and our pupil size and everything works. Oh yeah, right. If you hit Command Z while you're in play mode, the materials, then they'll disappear, so should be aware of that. So we're gonna save this, and then of course we can, keep on duplicating these, give them their own individual rotations, even scales if we want. So if I hit play, yeah, you can see, scale is functioning properly. So if we're, on our camera and you could see that eye to the left blinking out of existence, when we rotate the screen too far to the right. And that's how we know, our frustum culling is in fact working. Of course, since we're only culling based on the object position and not its bounding box, then if we're really close to the object takes up a lot of space on our screen. Then once its pivot is out of view, then it'll cull the object. So there's definitely room for improvement in the compute shader when we're culling. We're only culling based on a position, but we should cull based on a bounding box instead. And we can do like a spherical bounding box as well for our eyelids if we want. So if we have like a radius from the object position, then we just test whether that sphere is basically within the frustum. It would be we'd definitely take more computations, but if you don't want things to blink out when they're really close to the camera like that, then we could definitely modify this. We could also just turn up our frustum cull value to something like 2 maybe. That would also ease that effect a bit. We'd have to be really close to objects to see them blink out, pop out. But yeah, I'm not too worried about that. If you did want to implement bounding box frustum culling, then of course what you'd have to do is in the buffer here, we'd also have to, generally depending on if you're using a spherical bounding box or like a cube, what are bounds? They're just they're just if it's a cube, it's just 8 different points, but we only actually need depending on if we have uniform scaling for our object, we only actually need to input. We would only need 1 float value for like the bounding box size, and then you'd construct 8 points based on this scale value, which again, this we would set this through based on our object scale and everything. Oh yeah, I'm not also updating these bounds because actually, let me make sure that works. When I was debugging this, I thought that could have been an issue as to why we weren't having any objects drawn, but let me make sure that nothing gets cold while I... So yeah, we can still see objects. So our bounding box for all the objects is, it's working properly. I guess to illustrate the effect of this bounding box, I can comment out that method and just keep it at this default size, which is vector 3.1. So just a 1 by 1 by 1 cube. And right now that cube is centered on the origin. So let me see. Yeah, so once that bounding box centered on the origin, like we can't see it, but we know it's there. Once it's out of the camera's frustum, then all the instances of all the instances that we're drawing get culled like this. Oh, and one more thing we can do. So I was not sure of the best way to actually visualize these in the inspector. Yeah, so I was just using, since we have these eye objects with their own script attached to them, I was just drawing a sphere in the draw gizmos method, and then we can also draw a line that is in the forward direction. So we do, so its origin, its starting point will be this object's position, and then what do we want? We want this dot transform dot forward plus, so we want to add, just the forward vector to the transform's position, this object, like that. And so now we have, lines indicating which direction these objects are facing, or which directions our eyes would be facing, when we place them in the inspector. Can multiply this by 2 to make it a little longer. And yeah, if you want some more, like, I don't know, there's different methods we can use for this. We could also use on draw gizmos selected, so only the selected object will actually draw itself in the inspector. If we're placing, a bunch of objects like this by hand, definitely if you want to, like, I don't know, I never really have used, I haven't really delved too much into like editor scripts and, the gizmo visualization and all that, but if you want to learn more about that, I would recommend you check out Freya Holmer's video series, specifically, I think it's Intro to Tool Dev. She has like a bunch of really good free, just, YouTube videos that are like many hours long, all with very good info if you're trying to learn, as well as like shaders, writing shaders and code actually from scratch. It's also she has just really good resources for everything, so I would definitely check that out. But yeah, this was also an experiment for me. I'm by no means an expert in any of this, not even close. So definitely, if you have like problems with something or improvements for something, you should just tell me. But hopefully this was illustrative enough. Hopefully it was like a cool eyeball shader. Yeah, that's the main takeaway from this, I think. Oh, and one last thing we should do if we really want to, finalize everything is actually pass or create variables on our iManager script that are then passed to the materials themselves. So everything is just, in one place. All our parameters for our materials, essentially. And to do that, well, first off, in a C# script, we can add like a header or something. This just kind of like, this will sort of organize, your the script in the inspector when you're looking at it, but we can have a header for, or rather, I guess what I'm going to do is put a header down here and call it material parameters. And if we save that, now we'll see a, oh, huh, I didn't think that would apply like that to all 3 of these, alright, let me just add a, you can also add a space, I believe. Maybe if I just add like a space height 1, that'll fix that. Huh. Okay, well, so I guess if we write out our properties like this, then we're gonna have the header applies to each one, so I guess we'll need to separate these. Or at least separate, the first one, have the first one separate from the other 2. We could add, additional headers, if you want to organize things properly, like eyelid blank parameters, this. that's, so now we have a, a decently nice header for these next three parameters or these properties. So, I'm gonna just quickly just set up and get rid of properties we don't need in the script here. So we don't need this target or the material we don't need anymore. We don't need the target position anymore. Pass to the material directly. We don't need the eye rotation limit or the blink speed, frequency. But I'll keep the normal map and the color as well as the follow strength. And so we know that we'll need to pass these three parameters in from a script. So, for instance, this eyelid follow strength, it's a slider in the range 0 to 1, and this is the reference underscore eyelid follow strength. I might just call this eyelid. It doesn't have to be that specific. So yeah, so we have this eye rotation limit. I'll add another range modifier, and we'll do 0 to 1. Then we'll serialize this field, which is a private float eyelid follow strength. I'm going to default it to 1.5. Not 1.5. I need to default it to 0.5. My bad. But now, so now this appears, we have this in our inspector window. And if we want to pass it to the material every time the value changes, Unity has a method called OnValidate. This OnValidate method gets called whenever you change a value in the inspector. So what we can do is that when we call the OnValidate method, we can get our eyelid material and we'll set the float, which in this case, since we're not updating this every frame, we don't really need to worry about converting this property to an integer. So yeah, I'm just gonna write out the property like this as a string and then set the value equal to the eyelid follow strength. Yeah, and then we'll basically go through and do this for every parameter on both our eyelid material and the eyeball material. So I'll need a normal map and a color for the eyelid. So I'm going to create a private texture 2D, I guess. I'll call it eyelid normal map. Is there a default? Texture dot 2D dot normal texture. Yeah, so we do have I think we can set a default like this. This is just that default neutral direction texture. And then again, in our OnValidate method, get our eyelid material. We'll set a texture. That'll be the underscore eyelid normal map. Like that. And then we'll set it to the eyelid normal map. And we'll do the same for a color as well. Private color eyelid color equals color dot red as a default maybe. Color dot gray maybe. And then we'll do the same thing. Eyelid material dot set color. This is what it's called. Yeah. Eyelid color. That. Then those are all the parameters that I have currently for my eyelid. But you could definitely have additional ones. We should probably add a smoothness, but I'm not going to worry about it right now. And then for the eyeball, we actually have a lot more parameters here, but I'll get rid of the ones we don't need. So we don't need the rotation limit. I believe everything else we do need. Oh, and we don't need the target position as well. Let's save that. But yeah, so you would just go through and we would, so for instance, We would create another header here probably. Call this eyeball parameters. We'll create a serialized field, private. In this case, it's just we have a couple of floats, pupil size and edge hardness. So private float, pupil size. You can set a default to. Oh, so this one's also a slider in this weird range that we have defined. So we should probably set that up. So we get a range. Goes from -0.99 to 0.5. 0.5. Then we'll default it to -0.8 or something. Add the edge hardness, which is set to 50 currently. Pupil edge hardness 50. And then down in our OnValidate method, we'll take the eyeball material and we'll set a float, which is our pupil size. Set it equal to the pupil size. And then we'll also set the pupil edge hardness equal to pupil edge hardness. And yeah, we just, it's a little tedious, but we'll just go through every, all the iris properties now and then create variables for them in our inspector. Oh, looks like we can't, okay, so looks like we cannot set a default normal texture like this. So never mind. Should delete that, save it. But yeah, so then we, grab whatever textures we need here. For instance, the eyelid, I'll grab this. Eyelid color, I can set that. I don't know why these weren't set to the defaults that I set in the script, but set those something. And then just so we can actually see this working, let me just create a game object real quick. Just grab the eyelid. And then so we have this eyelid material applied. If we change a value in our script, we can see it being updated in the scene. Same for the normal map. Everything works properly. Of course, we won't see any of these properties being affected, and this is where there's room for improvement. How are we gonna what's a good way to visualize these parameters in the scene, since these are being calculated in a compute shader every frame? We could technically execute that compute shader and everything and draw the meshes indirectly from, we could do that while we're not in play mode, but it might be a better idea to just, I believe there's an option where you can, I think there's a way to make changes made in the inspector remain, changes to values in the inspector stay the same, once you exit play mode. So for instance, I'll go into play mode and then go into my scene view. And here I can control these parameters and stuff. You'll have to be careful because remember, when I hit Control Z, then the eyeball is going to disappear since I'm instancing it. So just be aware of that. But yeah, so if we change this to -0.7 and then exit play mode, that'll return back to 0.85. But I'm fairly certain there is a way to disable that effect, so the changes will stick in the editor. But yeah, I will leave that up to you to figure out. But anyway, that's it. That's all I've got.